all these lectures. First, I just want to say thank you to everybody here for just being such warm hosts for the last couple of months, especially to Shiraz and Sandy. It's really been wonderful to spend some extended time here on this. I'm going to tell you about the quantum Hall effect, and I'm going to tell you about a new approach, newish approach to the quantum Hall effect that I've been developing here with Carl, who's a student, and some work in progress to do with Nick Dorey. I used to be Nick Dorey's student, so it's kind of like 3 generations. Lots of you will be coming to these lectures, so you basically know as much about the quantum Hall effect as I do by now. But the reason I got interested in it is because it's really this beautiful bit of experimental and theoretical physics that includes many of the highlights of theoretical physics from the past 30 years. So it includes, obviously the direct approaches, things like the Waffling wave function, which we'll be looking at in the lectures, but it also includes, or it's connected to Chern-Simons theories and conformal field theories, and the kind of work that Witten did to do with knot polynomials, and just lots of utterly beautiful things in theoretical physics emerge in this simple experimental setup. So the original purpose of this project was to try and find closer connections between these different approaches to the quantum Hall effect, and in particular to try and find closer connections between the Chern-Simons theory and the Waffling wave functions, which is a little bit hand-wavy in the literature. So one of the things I'm going to do here is give a very precise connection between starting from Chern-Simons theory and deriving Waffling wave functions. But as we've gone on, we've realised there's quite a bit more to this. So we've realised that the approach we're taking is sort of a much more analytically tractable approach than the usual approach to the quantum Hall effect. So we can do calculations that you couldn't usually do with the standard approaches. And what's more, in this sort of latest project, we're realising that we've got more general classes of quantum Hall effects. So we're going to write down more general wave functions that, as far as I can tell, haven't been discussed in the literature. I don't know if they're experimentally realisable, but they're the quantum Hall wave functions that are equivalent to SUN Chern-Simons theories of various levels. So it's a very basic thing which we haven't been understood before. So at the end of the talk, I'll try to describe this to you. And I'm going to start on the next slide just by sort of telling you what the key player in this talk is. And ultimately, what we're going to do is actually derive this from various ways. But this is really what we're going to be talking about throughout the talk. So it's very simple. It's a matrix model. So it's a quantum mechanics 0+1 dimensions, and it has a UN gauge symmetry. So it's a gauge symmetry in quantum mechanics, which means it has a gauge field that I've called A0. This is just a UN gauge symmetry. And charged under this UN gauge symmetry are 2 fields. So there's a field called Z, which is an n by n complex matrix, and this is going to transform in the adjoint of the gauge field. And then there's a bunch of fields called phi I, and each of these transforms in the fundamental of the gauge field. So each of these is a column vector, an n-dimensional column vector, and there's going to be p of them. So it's a very, very simple model, as you can see. It has a UN gauge symmetry, and it also has an SUP global symmetry, which just rotates the different filaments. What else to say? The thing that's slightly odd or slightly unusual is that it has first order kinetic terms, not second order kinetic terms. And so we'll see exactly where that comes from. So we're not the...
Sorry, just to make sure, I guess because it's UN, you get a trace A0 term.
Exactly. So this term's also what they got. It's like a quantum mechanics Chern-Simons term, but it only knows about the U1 part of the gauge theory because of matrix. Background. It's a background. Exactly, it's a background charge, and we'll see exactly where this comes from. So we're not the first. Yes, please.
Excuse me. In the last term, you don't have an analogous term for the fundamental.
No. So this is the potential. Because these are first order, this is actually the same thing as the Hamiltonian. I do all the genre transform, just take this. And it's only... And we'll see exactly where all this comes from in great detail in this talk, so I just want to flash it up now. We're not the first to consider this matrix model. In the case where you just have one of these scalar fields, this was written down by Alexios Polychronakos back in 2001, and he wrote it down precisely as a model for the quantum Hall effect. And back then he argued that the ground state wave functions of this theory were the Loftin wave functions. So we're going to review that later in the talk. What I really want to do in this talk is twofold. The first part of the talk, I want to tell you where the matrix model comes from, which Alexios didn't know back in 2001. In fact, I'm not quite sure where he got it from. He just kind of wrote it down. We're going to derive this matrix model, and the basic idea is you start from a Chern-Simons theory in 2 plus 1 dimensions, and you look at the dynamics of the vortices in this Chern-Simons theory, and the dynamics of the vortices will be described exactly by this matrix model that I've just written. And if you start with a UP Chern-Simons theory in 2 plus 1, you get this SUP global symmetry. Okay. So that's the first part of the talk. The second part of the talk I think is going to be a bit more interesting because we're actually going to solve these matrix models. And we're going to review some of this old work to do with the fact that you get Loftin wave functions in the simplest cases. We'll look at the wave functions you get when you have a non-Abelian Chern-Simons theory, so when you have an SUP Chern-Simons theory. We'll see why these wave functions are much more tractable than the Loftin than the usual wave functions. And then towards the end I'll explain how these matrix models are really Wess-Zumino-Witten models in disguise, at least some subset of Wess-Zumino-Witten models. So for those of you who don't know, Wess-Zumino-Witten models are formal field theories in 1 plus 1 dimensions. And so I'll try in the first part to explain why you would expect them to be Wess-Zumino-Witten models, and then in the second part we'll see concretely how this works. Okay, so that's the plan of the talk. Any questions about where we go before we go? Yes, please.
All your Chern-Simons theories are in 3 dimensions, 2 plus 1.
Sorry, say that again.
Your Chern-Simons theory is always in 2 plus 1.
Chern-Simons theory is in 2 plus 1.
Yeah.
Matrix model in 0 plus 1. And it's a bit confusing. This is in 2 plus 1.
Yeah.
You derive the quantum mechanics in 0 plus 1.
And you get a 1 plus 1.
And then you show that's equivalent to a formal field theory in 1 plus 1.
That's already equals between each other.
Which is already known to be related to this in a different way. We'll sort of see this relation more directly. Okay. Yes, there's lots of different theories kind of bouncing around. But this is the case. Okay. Any other questions? Well, good. Okay. No questions? Okay. All right. So this is the theory we're going to start with. For the first half of the talk, to make things easy, I'm going to talk about the P equals 1 case. So that corresponds to a U1 Chern-Simons theory in 3 dimensions. And then for the second half of the talk, I'll tell you the generalization to UP Chern-Simons theory in 2 plus 1. The generalization turns out to be quite easy. All right, so this is the Chern-Simons theory that we're going to look at. It's a U1 gauge theory in 2 plus 1 dimensions, and this is the Chern-Simons term at a level k, where k is an integer. And it's coupled to matter. It's coupled to just a single complex scalar field, which has charge 1 under this U1 gauge theory. And the thing that's a little unusual, at least if you're used to relativistic field theory, is that this is non-relativistic coupling. So this is the time-like component, and these are the spatial components. So this means, firstly, that if you quantize such an object, just doing canonical quantization, the complex scaling gives you particles, but it doesn't give you any antiparticles. So it's just particles. Also, the dispersion relation for these particles, you can see here, it's energy equals momentum squared over 2m. Okay, so it's not energy squared equals momentum squared. It's the thing we knew in high school, right? Its energy is a half mv squared.
So these are bosons.
Well, these are bosons if you quantize them, but they actually turn into anyons because of the Chern-Simons.
The particle number is a good quantum number.
Yeah. Well, U1 is the gauged object, but yes, if you fix the number of particles, they change.
It's just non-relativistic anyons interacting with the quick.
The thing that's slightly unusual is, okay, so there's some interaction terms. I'll talk about mu shortly. The phi to the 4 interaction term is just a pointwise interaction between these objects in a non-relativistic setting. But I haven't put a general coefficient here. I've tuned this coefficient to be related to this coefficient. So that's slightly odd from just writing down an effective field theory. There's 2 ways to think about this. One, which is the way we arrived at it, is that this is actually a theory which admits a supersymmetric completion. It's odd because usually supersymmetry is related to relativistic field theories, but this admits a non-relativistic supersymmetry. It was written down by Leblanc, Lozano, and Min in '93. So that's kind of what drew us to think about this this theory. By the way, for those of you who remember my talk in Goa, I know it was a long time ago, I was talking about exactly the same theory, but with mu equals 0. So the only difference is term. Another way to think about it is if you set mu equal to 0, this theory, this coefficient actually runs. And this is the fixed point of this coefficient. So it runs in the infrared or conformal field theory with exactly this coefficient. So even if you don't like supersymmetry, there's really think about tuning this coefficient.
So you tune that phi-4 coupling.
Yeah.
But in a sense, you also tune the relative coupling of the phi-0.
Good. And I've also tuned this to this. That's exactly right. This is this is mu times particle number. So if I fix the number of particles, mu is it's not playing too much role in dynamics. Okay. This, however, is a background charge that's telling me I'm obliged to fix the number of particles to be something like that. So again, you're right. I've sort of tuned these two, and we'll see what role that makes. Right. So it's a slightly finely tuned Chern-Simons theory.
So in the supersymmetry theory, are these small phi's really promoted to capital phi because you need fermions, right?
Yeah. So you mean in terms of a superfield?
Yeah.
I don't think there's a superfield formulation of these kind of theories.
Which will play the part of fermions?
You've got to add some fermions.
Okay.
Yeah, and then there's another line with terms for fermions. So in fact, the way we presented this in the paper was as kind of a supersymmetric version of the quantum Hall effect, because we wrote down a supersymmetric Lagrangian and showed you had the quantum Hall effect. With hindsight, I think that's maybe not the best way to sell it, because the fermions don't really play much of a role. So maybe we should just throw them out.
So there are two values of phi to the 4 that are fixed points of the RG flow, right?
That's right, plus and the minus.
And is this the one that gives Arnav-Bohm scattering or the other one?
They both give Arnav-Bohm.
One of them gives Arnav-Bohm with an initial potential, right?
Oh, sorry, I know what you're saying. Yeah. Do they diverge or do they?
Yeah.
Do you remember the answer to that?
What's the theory of vortices?
No, but it's not the thing.
You said the coefficient is this. You said the coefficient of the analytic part to 0 or the non-analytic part to 0?
Yeah, we knew the answer to this back.
It doesn't matter.
I can figure it out, but maybe not in real time.
I mean, can I ask something which may not be related? But here you've chosen the sign so that it's an inverted potential at the origin, right? Because it's kinetic minus potential energy, if I'm reading right.
Mm-hmm.
So the potential energy at phi equal to 0 starts as minus mu phi squared, and then the classical minimum is a Wilson-Fisher-like minimum, right? At phi equals.
So there's the question that Shiraz asked, which I think is if you set mu equals to 0, because turning mu on is going to change.
Okay.
So I think I'll answer your question on the next slide. I'm not sure what the answer to Shiraz's question. It's one of those, right?
Yes.
Okay, so what's the physics? The background charge, the mu A0 term, is telling you you're obliged to turn on some fields in the vacuum. So the vacuum is very straightforward. It's just phi squared equals mu. And the magnetic field is equal to 0 in this vacuum. And you can look at the fundamental excitations, which are the excitations of these bosons. And it turns out they're massive, meaning that massive is a relativistic terminology. They're gapped. It costs a finite energy to excite it. But there are massless, there are gapless excitations in the theory, which are just the vortices.
Wait, so the gap just because of the mu phi squared term?
So it's this phi squared equals mu isn't quite the minimum of this potential. This potential has a minimum of negative, but it's more important to solve Gauss's law coming from the A0.
Uh-huh.
So, but yes, basically they're gap because of
Okay.
But there's gapless excitations, which are vortices. So the U1 gauge theory is the U1 gauge group is empirical, which means there are other excitations where the phase of phi, which is in the Higgs phase, has to wind asymptotically, and these are vortex excitations. These vortex excitations have a very nice properties. Firstly, usually in theories, if you have solitons, they solve some second-order equations of motion. Usually, everything solves second-order equations of motion. In this theory, it turns out the vortices obey first-order equations of motion, not second-order. So these are the vortex equations. This actually is just Gauss's law in this theory, so this is a constraint. The nice fact about the theory I've written down is that the vortex equations, the additional equation you need is just this, the phi is holomorphically constant. This is a consequence of me fine-tuning that phi to the 4 term compared to the okay, if you don't fine-tune that, it turns out you have to solve complicated equations. If you fine-tune, it turns out you have to solve just these simple equations. Okay, so these vortices have a number of properties, which I'll just state. Firstly, they don't cost any energy at all, so they're completely gapless. Secondly, the vortices are bosons if k is even, and they're fermions if k is 1. Again, you can just see that by some Aronoff-Bone type phase. And finally, the vortices are BPS. So BPS means different things to different people. One way of saying they're BPS is just that they're first-order equations of motion. Physically, the way you can think about it is there's no force between vortices. So if I take a bunch of vortices and I place them at different points on the plane, there's neither attractive nor repulsive forces. So from a condensed matter perspective, it's like being exactly on the midway point between a type 1 and a type 2 superconductor. Vortices just sit there.
These vortices carry the minimum magnetic field allowed by quantization?
Yes. And finally, I should say, if you go to the supersymmetric theory, these vortices sit in short multiplets rather than long multiplets, which is the other key BPS. Okay, so the BPS in vortices.
So that means the phi winds once.
Phi winds once, exactly. All right, so let me tell you the basic idea of what we're going to do. We take this theory and we throw in n vortices. Now, as I've said, you can put these vortices anywhere on the plane and you get a solution. The first thing I want you to notice is what the meaning of this term is for the vortices. Okay. So this term was a background charge in the original system. But by some version of electromagnetic duality, if you're a vortex, a background charge looks to you as if it's a magnetic field. Okay, so let's see how that works. This is the term in the Lagrangian, UA0, and by integration by parts, I'm going to write it in the following way. So I'm going to write it as J mu times just some constants. J mu is this combination of fields, which it's known is exactly the current that couples the vortices. In fact, you can see, if you look at J0, it's just F12, the field strength, and so the integral of J0 is going to give the number of vortices, because of the integral of magnetic fields. So this is the vortex current. This, meanwhile, is precisely what you would write down for a background magnetic field in the symmetric gauge. Okay? So it looks as if the current associated with vortices is coupled to a background magnetic field. The background magnetic field is what you would read off from here. So as these vortices move, they're moving as if they sit in a background magnetic field. Yes?
You said the natural state is for phi to wind around 1.
Yeah.
So when you say there's no force, that is on some long length scale then? Because
this is...
If I put two of them together, wouldn't I just think of them as winding twice in some ways?
Yeah. Let's... There's various issues about forces in this theory. Let's talk about the analogous relativistic theory. Then, as I'll review later, there are solutions where phi winds twice, say, but you get to put those vortices anywhere you like. You can put them on top of each other, you can move them apart a little bit. Anywhere you like, you have solutions to these equations. So they're very finely tuned equations, they have lots of nice mathematical properties that have been studied, some of which we'll use later.
Just maybe ask something which might be related, I'm not sure. The fact that the vortices are gapless and so on have these nice properties, that's a consequence of this finely tuned. Do we know enough to be able to say if you chose a somewhat finely tuned case, the vortices are presumably gapped?
Vortices will be gapped, and you would only get solutions depending on how you change the potential, if they all sit on top of each other, or actually if they're all infinitely functional.
And gapless means it costs no energy to create a vortex. It's the same energy as the vacuum.
It's very easy.
Yeah, I don't think there's too much to read into that, to be honest, but it's just a consequence. The reason it's unusual is because we're dealing with a non-relativistic. It's not like you can excite these vortices because they carry a conserved charge. So, these non-relativistic theories always decompose into sectors labelled by the conserved charges. Usually we think about particle number, But here particle number is infinite because we have this condensate in the vacuum. So now the decomposition is intersexolated by
Which means create a vortex, anti-vortex far away, and that carries no.
That's right. Yeah, that's true. All right. So this is the situation with vortices. But at the moment, these vortices can sit anywhere on the plane. We're making a big deal about that. I've been learning condensed matter slowly over the last few years, and one of the things I've come to realize is that it's important in condensed matter that the matter is condensed. So, and just having vortices dotted randomly over the plane isn't going to do anything. So we need something to push these vortices together to make some state of matter that we're interested in.
And so you have solutions for these vortices at arbitrary separations.
Yeah. Well, they exist. I don't have them, but you can prove rigorously that they exist.
Yeah.
So we're going to go back to our original theory and deform it just a little bit.
Sorry, but the one vortex solution is very simple.
Actually, that's not known analytically. It's very easy to solve using Mathematica.
It's just one way, ordinary differential.
It's an ODE which doesn't have, it can't be written, the solution can't be written in terms of special functions.
Okay.
You know, it looks like that. So we go back to the original theory in 3 dimensions, and we're just going to add a harmonic trap which breaks translational invariance, and what it's going to do is just encourage all of these vortices to collect towards the origin. Okay. So the harmonic trap is very simple. You go back to your 3-dimensional Chern-Simons theory that we started with, and you add the following term to the action. The mod z squared times b. It's pretty clear that if you have b, which the vortices carry, to lower the energy, now they want to head towards z equals 0. So what does this mean? It means that previously we had these vortices sitting anywhere at all of these were solutions. In the presence of this harmonic trap, the solutions are when all the vortices cluster together to form one big vortex. So these are actually solutions that Carl made on Mathematica. This is solutions with 7 vortices sitting at random places. This is the solution for, I think, 70. Is that right? I think about 70 vortices and the ground state solution. So you can see that it forms this kind of big object. You can show just with some back of the envelope calculations, the size of the object that it forms is proportional to n the number of vortices. In fact, the size of the object is a very good approximation given by this formula here. K was the Chern-Simons term, mu was this background charge density. And so roughly speaking, it looks like this sort of region where phi is equal to 0 in the middle, and then very exponentially quickly goes up to the phi being non-zero. So this is the phi equals 0 region, and then there's this exponential edge, and then it's phi equals mu mod phi squared.
So this corresponds to the term in the Lagrangian, which is mod z squared times mod phi squared?
This? No, it's mod squared z squared times... I see. Because of Gauss's law.
No, I was thinking I was a simpler question. What term in the Lagrangian is this?
This is the extra term I've added to the Lagrangian. Mod z squared times b.
It has to depend on your fields the way you did it.
This is what again? B. No, this is in 3D action, and B is the gauge field.
Oh.
It's breaking, there's no Lorentz in there.
So it's harmonic trap for what?
For vortices. Each vortex has a charge B, basically.
I'm sorry you said this, but so the vortices don't just sit in the center on top, I guess. Mm-hmm. They spread out.
If you know how to, you have one vortex which has some size. Now the other vortex comes, but you're solving some complicated partial differential equations. So what roughly happens is when it comes, they open up and form a bigger vortex. And then another one comes and forms a bigger vortex. And the vortex in the end has size proportional to the square root of the number of vortices. Here's one way to think about it. At the center of the vortex, there's a 0 of the Higgs field. Phi is 0. If I put 70 vortices on top of each other, at the center of the vortex, there's a 0 of the Higgs field of order 70. Okay? Because it has to wind 70 times, and so you get a 0 of order 70. Now, a 0 of order 70 looks very close to a step function. That's why this looks so flat and then... Alright, so here's the basic idea. What's going on in the middle here is the fractional quantum Hall.
Can you think of this z squared times b as a0, as an a0 which is proportional to z squared?
Why would you want to do that?
Because then the Chern-Simons term itself would give me Chern-Simons term is a0 times b.
Yeah, this isn't that.
Okay. Look, if I just turned on an A0, which was Z squared, that's not a solution. I'm not allowed to.
A0 is dynamical, so I'm not allowed to just.
But you try to turn on a background value and then fluctuations about that background. So you set that by boundary conditions. Maybe.
In some sense, I guess that is what I've done, but that sounds more. I'd be more nervous doing that because it's a gauge field. I don't want to be. Well, and the boundary conditions are set to. Okay, but it's not boundary conditions. Okay. This is the term.
Okay.
All right. So this is the basic idea. What goes on inside is the fractional quantum Hall effect. So why would that be? Firstly, we've noticed that these objects that are moving around the vortices, they feel like they're moving in a background magnetic field. Okay. As I mentioned, they're fermions if k is odd, and they're bosons if k is even. And we're squeezing them together in some way. Let's do some just sort of back of the envelope calculations to get a sense for why this might be a quantum Hall fluid. So we've got this this kind of new state of matter in the middle, which looks very uniform, I should stress. And we know that these vortices experience a particular magnetic field that I call B external. So just going back to basic Landau level physics, suppose these vortices were in the lowest Landau level. How many states would be in the lowest Landau level in this region? Well, this is something that we computed in the very first lecture. It's basically the number of states per unit area is proportional to B external, and B external was the same thing as mu, the background charge. But we know that the area of the vortex is given by the following. The area of the vortex is n times k over mu, which means that the number of quantum states within this region we expect to be capital N times k, but we've got exactly n vortices. So it means that if we think about lowest Landau level physics, the number of vortices in this is precisely 1 over k of the number of vortices that could be in the lowest Landau. So just this sort of very hand-waving heuristic argument suggests that what's inside here is a fractional quantum Hall state, a filling fraction 1 over k. And now our job is to try and find proof that that's
the first statement, how did that come there?
So the first statement was the vortices feel like they're moving in a magnetic field, which I call Bx. In a magnetic field Bx, the number of states in the lowest Landau level, we know how to compute per area, and it's just this. But now we know the area, so the number of states in this area is this, and the number of vortices is the So this is kind of the intuition, is what's going on inside of this is a fractional quantum Hall system. And now we want to try and understand this from different perspectives to see how the fractional quantum Hall physics emerges.
Does it tell you anything about odd versus even denominator fractions?
Yeah, it tells you the usual story that odd are fermions and even are bosons. Because the vortices are fermions and bosons depending on k.
So now to make this precise, you're going to quantize the moduli space of.
That's exactly what we're going to do. Yeah. Before I do that, there's one other thing I'm going to do. Let's just look at let's not look at the details of the vortices. Let's just look at what this state looks like on large distances. So remember, outside the vortex, this was the vacuum. The gauge field was broken. Inside the vortex, phi squared is 0 because, as I said, phi is basically a 0 of order 70 in the middle. Or if you have 10 to the 11 vortices, it's a 0 of order 10 to the 11. That looks just like a very flat phi equals 0 region. So in here, phi is 0. It's a good approximation everywhere. And meanwhile, there's a magnetic field which sticks through. But the key point is that inside the vortex, U1 is unbroken. And it's unbroken in a large region of space. Which means that the effective dynamics inside the vortex is just the Chern-Simons. But it's been known since the early 90s that this Chern-Simons theory is the low-energy effective theory for the fractional quantum Hall. It's something we'll review in the lectures next week. And it's very easy to prove just on general grounds that the Hall conductivity you get from this is precisely the Hall conductivity you expect of the fractional quantum. Okay? So what these vortices have done is the following, that they've managed, by putting lots of them together, you've got this region of space where U1 is unbroken. And you know that U1 Chern-Simons theory is quantum Hall physics. But then there's a boundary of that region where outside the U1 is broken. And so the idea is that this is the quantum Hall droplet And the edge of this is going to be where interesting edge effects happen. And outside is just some boring vacuum there. Okay, so we've dynamically cooked up this kind of droplet where you get quantum vortices.
Can I ask something? It's confusing me. It has to do with odd versus even. Your picture that, if you took 70 vortices that sort of come together, you get an order 70 zero.
Yes.
Sort of seems intuitively good to me for the bosonic.
It's a classical description.
It's classical.
Yeah, it's a statement about the classical field configurations. Whereas the boson versus fermions is a statement about what happens if you quantize those objects.
See, but, okay, maybe you talk about it, but when you quantize it, shouldn't there be a difference so that, okay, very far away, of course, it looks like 70, but really in the odd case doesn't quite...
We'll see when you quantize exactly what happens. We'll see the difference. All right, so that's kind of the long wavelength description. But now to make progress, what we really want to do is go and get the microscopic description, which is doing exactly what Shiraz suggested. You look at what the individual vortices are doing, all 10 to the 11th, and you try to write down the wave function for those vortices. Now, because nice things have happened, because I fine-tuned these vortices to have special properties, it turns out that's essentially a solvable problem. So let me explain how. So the first thing I need to tell you about is what's called a moduli space. It's something very familiar to string theorists, but I think not so familiar to condensed matter physicists. So the basic idea is the following. These are the equations we want to solve to describe vortices. And what we fix is the winding of phi at infinity. So we say that phi winds n times, and you want to solve these equations subject to that. Now, these were studied to death in the 1980s by mathematicians and by physicists. In particular, a mathematician called Taubes, who's in Harvard, who proved the following, that the set of solutions to these equations, there isn't a unique solution. The most general solution has 2 times n parameters. And it's very easy to understand what those 2 times n parameters are. They're just the positions of the vortices, n vortices sitting on there.
And when they're far away, that's precise.
When they're far away, actually for vortices it's surprising. You can make that precise regardless of where they are because you can identify positions of vortices by the 0 bit. It's not necessarily a good way to say where they are, but you have a specific way of saying what these two are. Okay, so the idea of the moduli space is the following. The moduli space that I'll call Mn is the space of solutions to these equations. So it's a manifold which has dimension 2n. It's a big manifold. The coordinates on these manifolds are called capital X. That's here. And the idea is that for every single point on this moduli space, there's a corresponding solution to the vortex equations where the vortices sit at some point. Okay. So if the words that are very tempting to say, and would be true in a relativistic context, is that the moduli space is the configuration space of vortices. In this context, it turns out that's not true. Because the dynamics is first order, not second order. Which means that actually this moduli space is the phase space of vortices, not the configuration space. So to understand the low energy dynamics of vortices, what we have to do is write down an effective action for vortices moving in this moduli space, in this space.
We'll just write down the symplectic form.
Write down the symplectic form, exactly. So this was a problem which was studied by Nick Manton back in '97, and then in a little more detail by Nuno Ramau and Martin Spates some years later. It wasn't quite the problem that I'm addressing here, but it's very closely related to this. And the answer is the following. It's a rather abstract answer, but the basic idea is the following: that you have this moduli space n, and the coordinates x are the 2n coordinates that parameterize this. And the action that you're after is the following. There's a one form over the moduli space, where d of the one form is, as Shiraz says, the symplectic form, which in this case you kind of roughly know what it is. It's a Kähler form on the vortex moduli space. It turns out vortex moduli space is a complex manifold, and there's a Kähler form. And meanwhile, the potential that we had, which was the thing forcing these objects to the origin, that also has a nice interpretation, because this was the potential, but you can show that evaluated on the vortices, this is the angular momentum of the vortices. So you have this large space, and there's two functions you need to compute on it, which is this one form fa of x, and this angular momentum, which obviously is a conserved quantity, over the vortex moduli space. So that's heuristically what the dynamics looks like. The problem is that we have to compute these functions f and j, and no one knows how to do that. Okay? We kind of know what they are geometrically, but this is a very complicated manifold, has a complicated metric on it, which doesn't show up here, but these objects are equally as complicated. So there's no explicit expressions known for either f or j. So we get a little bit.
It's not compact manifold.
It's a non-compact manifold, right? Precisely because the vortices can move differently. Okay. All right. So at this point, it looks like we've kind of ground to a halt.
So if you put the problem on a sphere, for instance, does it make it more perturbing?
It's related to the fact that there's just no solution to the vortex, even the one vortex equation.
On the sphere?
On the plane or the sphere.
Oh, yeah, yes.
All right. So this is the problem we want to solve. Thankfully, here string theory comes to the rescue. And there's a way to kind of get around the fact that we can't solve this. And it was something that, some work I did with Abi Kanani more than 10 years ago now. The basic idea is the following. For non-string theorists, I apologize. This is going to be string theory words, string theory words, string theory words, then we'll go back to condensed mathematics. So kind of decouple for a bit. Those of you who know string theory know it's one of the nice things about D-brane setups is that they capture soliton physics in a beautiful fashion using D-branes. And that's seen most clearly in the ADHM construction written in terms of D0 and D4 branes. And you get the moduli space of instantons in terms of some gauge linear model that lives in the D0 brane. Well, you can do exactly the same thing for vortices. So this is what I did with Abi Kanani, was cook up a D-brane model that captures the vortex moduli space, and you can think about the dynamics of vortices as some gauge theory which lives on the vortex world. And the gauge theory turns out to be the following. You have n vortices. What you need is a UN gauge theory coupled to two fields. Adjoint complex scalar z and a fundamental scalar phi. And the requirements is that z and phi have to obey the following constraint. So there's some numbers, but z commutator z dagger plus phi dagger. So I should say what this notation means. Z commutator z dagger is obviously an n by n matrix. Phi is a column vector, but you don't do phi dagger phi to make a scalar. Instead, you put them back to back. So you get phi dagger, again an n by n matrix. And this combination has to be proportional to the unit matrix. And then you divide out by gauge transformations which act in the following way. So Z transforms in the adjoint, phi transforms. So the claim of this paper that I wrote with Ami was that solutions to this equation modulo these gauge transformations is the vortex moduli space.
So that was like a D-term thing.
This is a D-term, yeah. So if you know about the ADHM construction, this is very similar to the ADHM construction, except you throw away half the fields. What you're left with is the vortex moduli space, not the instant moduli space. Okay, so let's at least do some counting to see.
What half do you throw away? Sorry, this would be the D-term.
Yeah, ADHM has a Z and a W, two complex field, and a phi and a phi tilde. So you throw away the W and the phi tilde. The F term then is immediately 0, and the D term reduces to 0. Let's just do some counting to see how this could possibly be true. There's an n by n complex scalar Z that has 2 n squared degrees of freedom. N squared and 2 complex. And then there's phi, which is a vector, so that has 2 n degrees of freedom. This is a matrix constraint, so this is n squared constraints. And then you divide through by gauge transformations, that's another n squared equivalences. So it's 2n squared from z plus 2n from phi minus n squared minus n squared. The final answer is 2n. So at least the dimension of solutions to this equation mod this is exactly the dimension of the vortex. So you can see that it's plausible. Okay. The nice thing about this description of the vortex moduli space is that it's much more versatile. So you can actually do things with it. In particular, the low energy dynamics of vortices is described by the following action, which is the matrix model that I started with on the first slide. So it's quantum mechanics. you put a first order kinetic term for Z and a first order kinetic term for phi with this sort of quantum mechanics Chern-Simons term. A0 is some quantum mechanics gauge field. The reason is that if you look at the equation of motion for A0, you get back exactly the constraint that I had in the previous slide. And meanwhile, this is the potential, and it's given by this precisely because the potential in the vortex was the angular momentum, and this is the angular momentum associated to Z goes to e to the I theta.
And by low energy, what do you mean? Is it like Landau level? Is it the same as saying the lowest Landau level?
Yes, and it took us a while to appreciate this. It's actually much better in this setup. So usually when you do restrict to the moduli space, there's some approximation about low small velocities. Here there's no approximation, meaning that if you can solve these equations exactly, you then plug the x as a function of t into the original vortex equations. They give you exact solutions to the equation of motion of the three.
For what?
There's no energy.
There's no low. So you're saying this and the matrix model are just completely equivalent?
Sorry, so there's two issues here. Firstly, this is the dynamics of vortices,
yes.
and there's no approximation of small speed.
Yes.
That's quite surprising for the usual things. This isn't quite equivalent to this description. The claim is that these are equivalent as complex manifolds, but the metric on them is not the same. Okay. What we'll see here is that we only need the complex structure to build the states, and so this is sufficient.
And what does that mean physically? You said something about low energy. I just want to understand precisely what that means.
I don't think that's relevant for low energy. That's just a statement about.
So if I had the original vortex problem,
Yeah.
Are all the states of that captured by?
All states are, but if you were to suppose we do non-relativistic vortices where the dynamics is somewhat richer, what you can show is that BPS states captured from this agree with the energies of BPS states because they're protected in some way, or they're reliant on the equivalence as complex variables. But non-BPS states.
I see. And then the matrix model describes only the BPS states or some approximation to all the states?
It includes all of the states.
But you only trust the BPS states. And what does BPS mean in this case?
So here I think we're on slightly better footing. It's not so much a question of BPS because there's no fermion, no Fermi zero.
Yes.
Instead what we need, the statement is this is correct as a complex manifold.
Yes.
And as we'll see, it's that which is going to be important. Basically the issue is that you need the right symplectic form.
Yes, but you've got something in the right topological club.
Exactly.
I see.
Yes. Not to turn it into a total string theory talk, but is there a deep brain construction which literally realizes the field theory you started with?
Yeah. No. So that's a good point. So what Ami and I really did was using the relativistic field theory and showed how the relativistic vortices arise. The reason we could apply it here was that the dynamics of this and this are both related to objects that appear in the relativistic theory. Because this is df where omega is the Kähler form associated to the relativistic metric, and this is the angular momentum. So I don't know how to cook up a deep brain setup for this, but I can use the results from the deep brain setup to extract what this is.
Sorry, David, just to be totally clear. So the dynamics, you said there's an approximation going from this to your D-term constraint equations. But from going from the D-term constraint equations to the matrix model, is that exact?
That's exact.
That's exact.
All right, so this is where we've got to. This is the first half of the talk, and promised the matrix model, which I claim captures quantum Hall physics, as the description of vortices in a Chern-Simons. All right, so the next step is we've just got to solve this.
No, I thought that was too strong because the D-term constraint just gives you the moduli space.
That's right.
So when you say it's equivalent to the matrix model, that seems too strong because here there's a notion of the metric also involved.
No, not metric, symplectic.
So, I think Sandeep was asking if you take the original symplectic form and restrict your constraint. Sorry, in the thing previously, you need an original symplectic form to restrict to your constraints in order to say that that is the same as the symplectic form of the matrix form. And
I see. So
what was the original symplectic form before constraint?
Good. So it was just Z daggers.
Yeah, so just standard dagger.
Okay, so that D-term constraint with standard kinetic energy terms reproduces the correct metric.
Not the correct metric.
No, not the correct.
Not the correct metric.
But okay, and then what does it reproduce? The relative is
supposed to be the same as a complex manifold.
No, but from here to the matrix model, if you use at this point you use the standard symplectic form.
Yes, and then this is just a
then
rewriting of that.
But that those two are just exactly.
All right. So our next goal is to solve this. And as I mentioned, this was written down almost 15 years ago now by Alexios Polypronakos, and there's a lot of work that was done on this 15 years ago, some of which I'll review now, and then I'll explain how we move forward.
Sorry, David, just before you motivated at the beginning that the vortices effectively are solving a quantum Hall type problem.
Yes.
Because they look like they're moving in a magnetic field.
Absolutely, right.
And that I should take as a qualitative statement, as a precise statement.
Yeah, it smells right, and now we'll see it's exactly right when we quantize.
Okay.
This is the sort of precision test of that.
So it's like particular. It's like obeying a quantum Hall problem with particular interactions and so on. Is that?
I think that's a good way to say it. Yeah.
Okay.
Yeah, and the interactions are no forces between forces. It's worth pointing out that if you read lots of the quantum Hall literature, they stress that the interactions between electrons are exactly what's giving rise to the fractional quantum Hall effect, and they pretend that it's the Coulomb force. And that's not quite true, because there's a class of toy models that Haldane wrote down called pseudo-potentials, whose ground states are exactly the Laughlin wave functions. But those toy models have the property that there's no forces between particles until they sit very close to each other. So they're sort of like delta function forces. This is a little bit like that, in the sense that there's no forces. But now, what interactions they are come from the non-linearities of these vortex equations. So it's a little more subtle. All right, so how do we solve the matrix model? It's dead easy to begin. We had these two fields, Z and phi, but they came with first order kinetic terms, which means...
Are we still doing U1 or are we doing UN now?
We're still doing U1, and then we'll do the non-Abelian.
So let me ask you, the adjoint field has played no role so far, right?
Adjoint field is capturing the positions of vortices,
Oh,
the Z.
thank you.
Yeah, it's like D-brain physics. The eigenvalues are capturing the positions of vortices.
And some of the phi's are like zero force strength or something.
Exactly. The phi's are the zero form, the analog of the zero form strength. All right, so we've got Z's and phi's, but each of them comes with first order kinetic terms, which means that the momentum conjugate to Z is Z dagger, and the momentum conjugate to phi is phi dagger. So if you quantize the Z's and the phi's, where A and B are now the labels that run from 1 to n, UN gauge labels, Z comma Z dagger is 1, and phi comma phi dagger is 1. So you just get a bunch of harmonic oscillators. Except, before I go to the except, so you introduce the standard vacuum state 0 that's annihilated by Z's and phi's, and the Hilbert space is just created by acting with Z daggers and phi. Okay. Except this is a gauge theory. And because it's a gauge theory, you have a constraint coming from the Gauss system. And the constraint is this formula that I wrote down previously. So we need to somehow impose this constraint on the Hilbert space. And you should think about it in sort of decomposing into two parts. It's a UN gauge theory. So think about the SUN part and the trace part, which is the UN part. In the SUN part, this constraint is basically telling you that all states should be singlets under SUN gauge. Meanwhile, the U1 part, which you get by taking the trace of this, so you take the trace and the Z decouple, and the U1 part says that phi dagger should have a particular number of excitations, where the number is k times the trace of this, which is n. And then there's a slight subtlety because you have to normal order the phi dagger. So when you swap them around, you get a k minus 1. Okay.
So the Z's, Can you remind me, they were complex?
They're complex, yes, and the phi's.
And the phi's. So now if the analytic phi is a creation operator, the anti-analytic guy is a destruction.
Yes.
And so you can only create states of a given charge.
Yes. Yeah, exactly.
So negative charge states don't exist in your thing.
That's exactly it. So what's the game? You want the Hilbert space consisting of phi daggers and z daggers acting on 0. But the number of phi daggers is fixed to be this. Okay. So you need to construct SUN in invariant states with a fixed number of phi daggers, and then the energies of those states is given by the potential term, which is the Hamiltonian, which just counts the number of z's.
And phi didn't contribute to the energy.
Phi doesn't contribute to the energy because the energy was to do with angular momentum, and the angular momentum is just changing the phase.
So all that phi is doing is saturating the background charge.
Yes, that's the only role it plays.
Yes.
Okay, so we have this sort of interesting group theory problem. You've got to fix some number of phi daggers, but you only pay energy cost for z's. The subtlety is the phi daggers have to form SUN singlets. But you only have phi daggers, you don't have phi's to play with. Because as soon as you introduce a phi into the game, it's just going to kill your state, because the vacuum is annihilated. So you've got a bunch of phi daggers, each of which transforms in the fundamental, against the energy fundamental. And the only way to form a singlet out of a bunch of phi daggers is by a barrier. So you have some epsilon symbol, epsilon A1, A2 through to AN, and then you put n phi daggers. Except that's a problem because the phi's are bosonic. So if you just do that, it annihilates by statistics because the phi daggers commute with each other. So the way you can build states...
So we're not doing U1 anymore?
We're doing U1 Chern-Simons theory in 3 dimensions. But with n vortices, this is UN...
I see. So the matrix model is... I see.
Yeah, exactly.
Okay.
The non-Abelian Chern-Simons theory turns into the number of phi's that we have. Okay. So what's the final state? The states you end up with are the following. You've got a baryon, you put a bunch of phi daggers, but now you've got to insert z's here precisely so these things aren't the same, so they don't disappear by statistics. So for each phi dagger you can insert a z, and the number of z's you insert here has to be different from the number here, different from the number here, and so on, so that you have a state which is a singlet and is non-vanishing.
Can I ask you this? Now the Z daggers, of course, contribute to the charge.
Contribute to the energy, yes.
But not to the charge.
No.
That charge constraint is...
No, the charge constraint is only the phi's, because you take the trace, and this vanishes with the trace, because it's in the charge.
Okay.
Alright, so the final state you end up with has sort of these interesting combinations of phi's, and it's very nice the way it works out. You're obliged to put a certain number of phi's in. But then just by anti-symmetry, the SUN singlet condition, that obliges you to put some number of z's. And you pay energy cost only for z's, not for the phi's. So the smallest energy state has no z's here, and then 1 z, and then 2 z's, all the way up to minus 1 z's. And in the state with k minus, where you had Chern-Simons level k, you've got to raise this to a k minus 1 power to have the right number of charges. Okay? So this is the ground state.
How do I simply see the powers of z have to be different?
Because it's
Epsilon.
so
Otherwise,
yeah. So this would vanish just because these are not. And this is actually something else. So you've got to have different objects, different objects. So this is the ground state. This starts to look very familiar, okay? Because the Laughlin state, which we met in the last lecture, is given by this. And if I expand out this van der Waals determinant, I can write it as an epsilon with ZA1 to the power 1, ZA2 to the power 1, through to ZAN to the power n minus 1. So this Laughlin state is very, very similar in structure to the kind of state we've written down above. Except it's not identical.
Sorry, but even just at the level of an analogy, what role are the phi's playing for?
Nothing at all. They just disappear. So it's not identical, but you can see the same kind of structure appearing. One reason it's not identical is that the z's here mean something very different from the z's up here. Right? The z's here are coordinates of the electrons. The z's here are like creation operators for electrons. They're not numbers, like here. They're operators which are acting on a vacuum. So to make this analysis more concrete, we'll have to think about a way to parameterize these wave functions in terms of numbers z.
I thought the eigenvalues of z would roughly be the location.
Exactly. So that's the kind of analysis we have to do.
So, and with this matrix model, if you wanted to just count states as a function of energy, that would be easy to do, right?
We've done it, and I'll tell you in this. Yeah, compute the full partition function. Yeah.
Right. And is there something to compare with for the quantum modification?
If you compute the partition function of this, you get the partition function for a chiral Moser, which you can also get from your Loughlin states because it's the thing that runs around the edge.
So if you think of all the states living at the edge,
it's not so clear.
Okay.
All right. So how do you do the map between this and this? Well, there's a beautiful paper by Karabali and Sakita back 15 years ago, and they showed there's various different ways to parameterize this Hilbert space. But the obvious one is the following: you take Z and you diagonalize it. You can't diagonalize it with a unitary matrix because Z and Z diagonal. You diagonalize it with x, z, x to the minus 1. But you write it as z1 to zn down the diagonal. With that parameterization, you then translate it into a wave function using those coordinates. And what they show is that it's almost a Loughlin wave function, but not quite. So specifically, they show that in the case of k equals 1, which corresponds to a fully filled lambda level, what you get is exactly the Loughlin wave function. And in the case of Philip fraction 1 over k, what you get is this state here is equal to the Loughlin wave function when these particles are far separated, but differs from the Loughlin wave function as the particles come close together.
Sorry, just to understand. So the eigenvalues of z, in the way you're saying, will become the coordinates.
Exactly.
But what happened to the phi's?
They just disappear, right? They're going to play a role in when you've got more than one of them, but basically they're not carrying in any information. Because the number of phi's is fixed.
Okay, so in that sector you compute it, and then, but doesn't that result in there's no coordinate or something corresponding to phi?
No, what we're saying is all states in the Hilbert space have exactly the same number of phi's excited.
Oh, I see. The phi daggers give some overall factor.
When you have different kind of phi daggers, then they're going to play a role. But when you just have a single one, there's no
It
information.
comes with some label, right? A1.
Which is a gauge.
It's a gauge degree.
So you're integrating a gauge.
So what you're supposed to do is take this ground state wave function and evaluate it on the appropriate state in a basis of eigenstates of z, etc., and then the phi's disappear.
Yeah. Okay, so there's a class of states here which look a bit like the Loughlin wave functions when electrons are far separated, but not like Loughlin wave functions when they're close together.
the phi's they're like Wilson lines, right?
You're just going to be exactly Wilson. So if you read this paper, they're a bit disappointed about this. They say, oh, we haven't got the Loughlin wave function. Maybe we can do something else. Maybe we can change our matrix model. Maybe we can change the map. It's really important to get the Loughlin wave function. It's completely the wrong attitude. Because as I tried to stress in the lectures, there's nothing special about the Loughlin wave function. It's just an easy wave function to write down that captures all the right physics. It's in the right universality class to have the right anyons, topological order. So this is another wave function that is very close to the Loughlin wave function, except it's easier to deal with. So this is a wave function where we can compute analytically what you can't compute with the Loughlin wave function. So what they should have done was just embrace this and say, let's move forward. This is a better thing than the Loughlin wave function for certain purposes. So let me explain.
So if you ask, which is probably a stupid question. Not every complex matrix can be diagonalized.
No, there's a set of measures zero that can't be, and they worry about this in arguments.
So there's nothing interesting that happens with these matrices that can only be good for the triangle. Nothing nice happens. No new states localized.
No. Okay, so this is the Loveland wave function. As we saw in the last lecture, there's more to quantum Hall physics than just the ground state wave function. You care about the excitations. And the most interesting excitations are the quasi-Hall excitations. Well, these also have a very natural interpretation in this setup, which is one of the things Carl and I realized. You take these ground states and you multiply by the following determinant operator, where Z dagger is the operator and eta is the position of this state. This was inspired by giant gravitons. If you do this, this we claim is the quasi-Hall particle, the quasi-Hall wave function, and in particular at large distances, it agrees exactly with the Loveland quasi-Hall. If you want a bunch of them, you just multiply by a bunch of these determinants.
I'm not understanding at all. Why is this? I thought a Hall was like removing a particle.
Hall is, one way of thinking about it is in the eigenvalue language. If this is multiplying the wave function vanishes when Z gets close to the position eta. But that's particles being excluded from that region, which is up there.
But does it change the number of?
No. The whole wave function just kind of swells a little bit, leaving a deficit in some region.
We had exactly this kind of.
You move it in a circle, the wave function picks up a Berry phase, where the Berry phase is the overlap of the quantum Hall differentiated with theta, where theta is the angle we've been moving around, and then integrated over values. You then compare that Berry phase to what you would expect from an Aronoff-Bohm experiment, where you take a particle with charge Q quasi-Hall and move it in a circle, it captures this flux, so you expect, well, we know how much flux is in there, so you expect that theta is given by the following functional form, which should go as R squared times the charge of the quantum. Now, in the last lecture, we did this for the Loveland wave functions, and you can't compute this overlap in that case. So we had to use this beautiful plasma analogy to show how you can get around being unable to do it. Here, it turns out that you can actually do the calculation explicitly, because we have a slightly different wave function written in terms of coherent states. I should say, it's not an easy calculation to do, but Carl somehow succeeded. It involved lots of staring at horrible books on symmetric polynomials. But you can do it. You can do it analytically. And the answer is completely horrible. You can see it's some ratio of hypergeometric functions. But it exists. And if you plot this horrible function, you get the following red line. What you can't see, unfortunately, is the black line. So the black line is what you would expect, which follows this precisely until here, and then the black line continues. What's happening here? So this is the Berry phase. This is the distance the quasi-Hall is from the origin. And what's happening here is the quasi-Hall is basically leaving the quantum Hall. So it's just no longer going through. Okay, so this is exactly the kind of calculation you would love to do for Loveland wave functions, but you can't. You can do them for these other wave functions.
So there, of course, what you're interested in is that regime. Yeah, not when once it leaves the.
Leaving is slightly misleading. What really happens is as eta approaches the edge of the disk, all of these functions degenerate. So eta equals the edge of the disk, and eta equals infinity is basically the same state in the Hilbert space. So there's kind of a singular representation in the Hilbert spaces.
I mean, you're interested before you get there.
But you're interested in this, and from it, of course, you can read the charge of these states, and it's exactly the fractional charge. Okay, the same is true for the analytic statistics. If you remember the last lecture, the game now is you take two quasi-Halls, you move one around the other, you compute the extra phase that you get due to statistics. Again, we couldn't do it for Loveland wave functions, we can do it for, Carl can do it for these wave functions. And the answer is, again, something even more. Ratio of confluent hypergeometric functions. This is the statistical phase, and you can see that this was actually plotted for a k equals 3 case. This lovely plateau in the middle there, telling you that these are anyons with the right statistics. Again, two edge effects. This is when it leaves the disk. This is when this quasi-Hall comes too close to this quasi-Hall. You start to see the interactions between.
What's n?
Sorry?
And what is it?
Where is n?
The hypergeometric. N.
Oh, sorry, little n is capital. All right, so this is what I promised. You start with a U1 Chern-Simons theory. you look at the dynamics of vortices in some detail, you can show that one, they give essentially the Lofting wave function, and two, they give the Lofting wave function in a slightly different form that's analytically tractable. So better for certain calculations than the original.
Okay, can I ask the obvious question? Which is, if you took your wave function for 20 particles and stuck it in, is it variationally?
I would love to know the answer to that. Yeah, so it's more analytically tractable, but is it close to the real? Yeah, I don't have the ability to. I should probably get in touch with some quantum Hall people and just check. Yeah. In the lectures I was kind of downplaying that numerical. Maybe I was partly biased by the fact that I've got a different wave function, which I like. Okay, so any questions about this? Look in detail at the horses. You really get all the quantum Hall physics. So let's go on and do something new. Let's look at the non-Abelian case. All right, so I'm not going to go through all of the story. The basic setup is the following. You start with a 3D Chern-Simons theory called a UP non-Abelian Chern-Simons. You work out what the dynamics of vortices is. In the same way, the dynamics of vortices is given by the following matrix model. Again, something I worked out with Annie long ago. It's exactly the same, except now you have P of these scales. Okay. And it sort of makes sense. The matrix model now has an SUP global symmetry, so it's capturing the UP gauge symmetry of the 3D theory is manifested as SUP global symmetry. This is the constraint. You can see that you just now have exactly the same P of these. And now we play the whole game again. We try and solve this matrix model and figure out what the dynamics is. I appreciate I've been talking for an hour now. Is just go on.
Okay, like 1:15 maybe, if that's okay.
That'll be easy. All right, so there's a whole bunch of questions that we can ask. What are the wave functions? What's the partition function, which I didn't mention previously, but we know now how to calculate. Finally, the question we really wanted to ask is what are the non-Abelian anyons, and can we analytically determine their braiding, meaning what happens as you swap them around? Because that's a question which has not been fully solved in the quantum Hall language. So we've solved the first two. It's taken us quite a long time. We haven't really got anywhere with this question yet. So let me tell you the answers to...
So understand the third question. What do you mean, what are the non-Abelian anyons?
So firstly, what are the analogues of those det z dagger minus eta states? And once you've got them, what happens when you swap them?
Right.
We don't know the answer to either of those questions. Okay, so all of this is work that Carl and I have been doing with Nick Dory over the past few months. Let me firstly tell you about the wave functions. It took us a long time to figure out these wave functions, because you can write them down very easily from this. What took me a long time was reading every paper in the quantum Hall literature to see what the hell they match to in real quantum Hall physics. And the answer is that they sort of match, but I honestly think there's something not. So let me try and tell you the issue. Each of these vortices, which is now like an electron, now carries a little spin degree of field, which tells you how it couples to the UP gauge symmetry. So each vortex comes with a finite dimensional Hilbert space, which is what you mean by a spin. If the UP gauge theory is a U2 gauge theory, these things are labelled by what you usually call spin. Spin half, spin one, spin three halves, and so on. But in general, they're labelled by an SUP spin, how this internal thing couples to the SUP gauge theory.
Sorry, I got a bit confused. The P here labels the rank of the Chern-Simons?
P is the rank of the 3D Chern-Simons theory.
Okay.
And also appears as a global symmetry in the vortices.
So it's just that the vortices have to wind in U1, but they can do that in any direction.
Yeah, exactly. So they have a little internal degree of freedom.
Well, I mean, sorry, just to connect, earlier you were in U1.
Yes.
And then you had a P, which was the number of phi fields in the...
No, there was no... When we did U1, there was no P.
Okay.
P was gone.
Okay.
So if you have UP, you have P phi fields in the vortex.
Okay.
All right. So let me just. So what happens? Each of these vortices carries a little spin degree of freedom. The overall wave function is always a spin singlet. So the spin degrees of freedom are paired up in such a way that you get a singlet under the SUP. But it does that in interesting ways. So let me just give you some examples. By the way, if you're not familiar with quantum Hall physics, this might be throwing names in, in which case so I apologize.
So just in the matrix model, are you going to put the SUP singlet condition?
No, the ground state is an SUP singlet. You don't put it, it just happens to be the case.
But if you compute the partition function, you're going to insert that as a constraint?
No, we'll compute the partition function again.
Get SUP non-singlets. Was that allowed in the original?
Yeah, SUP is a global symmetry and there's no Gaussian rule. It's not SUN, not UN.
Yeah, I understand. From the point of view of the matrix model, there's no reason to impose it.
Yes.
But I thought SUP was a gate symmetry in the original Chern-Simons description.
I see what you're saying. No, in fact, consider the following. Suppose I just put in I misled you slightly. Suppose I put in a single vortex. Single vortex carries a fundamental quantum number.
And that's fine.
And that's fine.
Just because it's non-compact space.
Exactly. But when I say singlets, the reason I misled you, you actually need a number of vortices which is divisible by p. Then you get singlets.
This is creamy. No, not by k, by p. Why?
They form variables, basically. Okay. Yeah, think of it this way: each vortex roughly transforms in the following way. If you put p of them together, you can get a variable.
So, but you are imposing SUP. So you are imposing the original the SUP singlet condition in the original.
No, I'm saying that if you put in the number of vortices, which is divisible by p, the ground state is a singlet.
Oh,
it's a state about dynamics.
Okay.
But do you have to put in a number of vortices?
No. So if I put it, we'll see what happens when I put it in vortices.
But if you study the original theory on a sphere, then there would be more complicated.
There would be, but I don't know, or on a torus, but I don't know how to write down a matrix model description for things on compact spaces. It'd be interesting to do. Okay, so what do you get? Let me just give you some examples. If you look at the the U2 theory in 3D at level k equals 1, you get what's called a 2-2-1 helper in state, which is a state for spin half particles and so on. If you look at SU2 at level 2, you get a very famous quantum Hall state called the Moore-Reed state. It's slightly different from the Moore-Reed state. It's actually the Moore-Reed state for spin 1 particles, where the singlet, each pair of particles sits in a spin 1 singlet. But it's roughly the Moore-Reed state.
And sorry, just to understand, so these are proposed wave functions for various values of nu, etc.
Yes, exactly. Yeah. And so this is the quantum Hall of Fame of wave functions, and all the famous ones we're basically finding. For SUP, you get things called
there are, of course, wave functions for a totally different problem, not a non-Abelian. For the electrons with at most U of electron in there.
So, of course, that's always the case, even for the Luther states. So these Chern-Simons theories we're starting with are the proposed effective descriptions for these wave functions. But there's some emergent Chern-Simons theory. We're finding a way to more concretely start with that Chern-Simons theory and relate them to the wave functions that people have proposed.
I see. You mean these non-Abelian Chern-Simons were proposed as the effective energy description for these cases?
Yeah. Although there's some confusion. And the recent paper by Seiberg and Witten last week has an appendix that I think clarifies a lot of the confusion in the literature about what the right non-Abelian descriptions are. And quite how that ties up with what I haven't figured out. But it's just to say, I think this is at the level where quantum Hall people are at, trying to understand non-Abelian Chern-Simons theory. We kind of, I think, have something new to say.
So you're saying that the relationship between the Chern-Simons and the actual quantum Hall effect is that the actual quantum Hall electrons should be thought of as vortices of that Chern-Simons thing?
Yes, which people knew.
Which people knew, right.
The novelty is to have control over those vortices at quantum state.
But moreover, I don't know, when we did our stuff, I used to go around asking various people, I didn't ask too many, where do non-Abelian Chern-Simons show up? And usually people say, oh, never. Or maybe in the transitions. Or something.
SU2 and L2 is
very famous non-Abelian states.
Yeah. So, there was no so really they can map and argue with the energy dynamics of non-Abelian Chern-Simons.
Yeah. It seems to me to be a mess in the literature. The original paper is by Fradkin, Wilczek, Nyack, and Sven. Yeah. And I'm not sure it's fully correct. I think there's some things are right and some things they've kind of screwed up, but I think the things they screwed up are corrected inside my woods. One point I'd just like to say, the proposed non-Abelian theories for Riemann-Zai states are actually SU2 at level P. And And we're finding they arise at SUP at level 2. So it's smelling very much like this is some level rank duality in a way that we haven't found.
And if you were to, I know you're non-relativistic, so on, but if you were to conform the theory of the original Chern-Simons level,
yes,
then these vortices would be dual to monopole operators. Is that right?
I'll say yes, but there's another kind of vortex in that theory called a Jakiv P vortex that I don't understand. Let me say yes, but maybe no.
Really, but by monopole, you literally meant is something localized in time as well. Did I understand?
Well, look, if you're in the Higgs phase, the monopole operator is the thing that inserts a single vortex. But it can be described.
Okay, only if you make it very.
I was just thinking of the state operator.
Doesn't it seem different? Just the energy or whatever for the vortex will go around time, and for the monopole would be more complex.
No, I mean, it's
all operators are localized in space and time. The electron operators are localized in space and time.
But in the conformity theory, there's a state operator. Operators are localized, but states are not. There's clean matter. So in that sense.
Okay, all right.
Okay, so all of this is to say is that if we look at the non-Abelian cases, a lot of the interesting quantum Hall wave functions that are well loved in the literature are there, but we have a whole bunch of new ones as well that just don't matter very much. Yes?
One should probably just point out to Sandeep's question that no one has actually graded and seen the non-Abelian nature in experiments. These are all proposed states for particular quantum halls.
But this state has you can see by shot noise that it's got charge over. So there's compelling evidence.
There's compelling evidence.
Okay. So let me move on. We want to look at the excitations of these systems. So what do we have? In the bulk, remember, we have this sort of regime of vortices, and in the middle there's an unbroken, now UP Chern-Simons. And then there's an edge to this where the vortice is stored. Now it's well known that if you take the non-Abelian Chern-Simons theory and put it in a manifold with boundary, there are edge modes which are described by a Westermino-Witten, 1 plus 1 relations. So given that our quantum mechanics is supposed to describe the interior of this, somehow it should know about the Westermino-Witten mode of the boundary. So the question is, does it? So how do we see this? Well, we can see this in a bunch of ways. Firstly, we can construct explicitly the current algebra in our quantum mechanics. So I won't show you the details, but if you construct the following objects, Z and phi's are the objects in the matrix model, and you construct the following gauge invariant objects in the matrix. Then with a lot of work, again due to Carl, you can show that in the large n limit, meaning that there's 1 over n corrections to this, these obey exactly the Catch-Moody algebra. Except there's a shift in the central charge here. So the central charge isn't k, but it's k minus p. Now, we've seen this before. When you do the normal ordering in that Gauss's law, we had a k goes to k minus 1. This is the version of that, k goes to k minus p. And we don't understand it, because any shifts that happen, well, actually there shouldn't be any shift at all here, but shifts are usually k goes to k plus p, if anything at all. So this is something that we're still puzzled about too. Okay, so we can see that there's a Catch-Moody algebra hidden in this simple quantum mechanics. That's very nice. But we can do more.
And Z to the M really had M units of activity.
Exactly. So it's the right thing.
Yeah.
So we can also compute the partition. I should say that we were chatting with Nick about what we were doing and how we were excited and the Westermino-Witten models. Nick has been working on spin chains for the last 10 years and somehow just knew that the answer to this knew how to compute the partition function. He mapped it to spin chains in a way that I don't understand at all, and I now realise it's not necessary to understand. Is there a question? Hello!
Yeah. So, about your previous slide, so at what you get is finite n?
At finite n, you get this plus 1 over n corrections.
Yeah, but what is this? Some finite n version of top-model algebra, some deformation of top-model algebra?
I have no idea what it's nothing we've seen before. Do you have an answer to that?
It's a mess as far as we know. We don't have any control over it.
It's nice plus 1 over n corrections times mess.
But I think it's asking that experience entirely in terms of J's, or is it something else? Is it a non-linear deformation?
It's non-linear in J's.
But it can be written entirely in terms of J's, no other objects.
Yes,
that it's been brought out that way.
Perhaps not. I have to check. Perhaps not.
Maybe it has a
Yeah.
Then that's
Does that answer your question, Logan?
Okay.
Yeah, I think it does require this.
Okay, so we can also compute the partition function. At least Nick can compute the partition function. So what's the?
But it's just counting inputs and counts, right?
Yeah.
Okay.
Yeah. That's all it is. So the partition function always just counting.
No,
But it doesn't mean they're easy.
no, in free theory it's always
Gauss's law is hard. Yeah, so let me tell you the answer. So what's the partition function? You'll trace over all possible states in the system. This is what you would use, T is what you would usually call e to the minus beta. Okay? E to the minus beta times the energy. E is the energy. And then because we have this SUP global symmetry, you can include fugacities for the U1 Cartan elements of that. So X are the fugacities and J are basically the Cartan elements for different bits of U1. So telling you the angular momentum of states on the SUP. And what Shiraz says is completely true. We have a free theory where it's trivial to compute, where it's fairly easy to compute the partition function. And then you impose Gauss's law. And the way you do this is you introduce, okay, so we've got fugacities for the SUP, but we've got this UN gauge symmetry. So what we do is introduce fugacities for the U1 parts of the UN gauge symmetry. These we're going to call omegas. We figure out the partition function for the adjoint and the phi, which actually you can see very clearly where this comes from. The adjoint costs you energy 1. That's why there's a T. And each adjoint you could think of as the A times the bth element of the matrix carries charge +1 under A and -1 under B, which is why there's an omega A divided by omega B here. Meanwhile, for the fundamental, it doesn't cost you any energy. The fundamentals have charge +1 under the UN and +1 under the SUP. Okay, so this is kind of the basic form for the free theory. You plug these into here, and then integrating over the W's, that's the UN, imposes Gauss's law. And by picking the choice of pole here, you get to impose the constraint of the level of charge on the right-hand side of Gauss's law. And this is just some Harmesh effect. Okay, so this is the way you do it. For the U1 theory, it's very simple. Even I can do it for the U1 theory. The U1 theory, that shouldn't be there, of course, for the U1 theory because there's no SUP. And the answer you get is just the following. This is the partition function for a chiral boson. At least in a limit where n goes to infinity, this is a partition function for a chiral boson. And it's been known since Wen's work from the 1990s, that's precisely what you get if you just enumerate all excitations above the voltage. Because there's chiral boson. Okay, so for a U1, we just reproduce standard physical physics. For SUP, I'll tell you the answer. It's, Shiraz says it's easy. It's
easy to write on a matrix model. Maybe hard to actually do
it's
it.
computing it. That's hard, exactly. And this one is, so what we do is we expand these in Chern polynomials. This one is very easy. This one needs a result from the literature that I don't even understand the paper. It's some huge, horrible mathematical physics paper that Nick somehow knew about and extracted the relevant physics. So what I can do is the following. I can give you a suggestion for what the answer is. We know the exact answer, but we know the exact answer only in terms of polynomials that I don't understand. Each of these polynomials has its own Wikipedia page, so it's fairly well known, but not by me. So what's the answer? This is just the chiral boson effect. Okay? What we're doing here is expanding the rest in terms of Chern polynomials. So if you remember, Chern polynomials are the characters of UN representations. And now we're expanding them out, I guess, in the SUP, not the UP. Okay, so we're just expanding this in SUP Chern polynomials. What's odd is, what I really don't understand with these objects here, these are things called Koster polynomials. And the point about Koster polynomials is the following. If you give me 2 UN representations, I can hand you back a Koster polynomial. At least I can Google, and if somebody's calculated it, I can hand you back. They're not known in general, they're quite complicated functions. The way they originally arise is in terms of relating Chern polynomials to things called Hall-Littlewood polynomials. So whole Littlewood polynomials are symmetric polynomials which are known to have a well-defined definition. Schur polynomials there's a relationship between them given by construct.
Wait, are you particularly interested in the Lagrangian limit?
Yes. And things are known about this in the Lagrangian limit.
Yes, so then it should just be a saddle bumper.
Let's chat about it, because as I'll tell you, the Lagrangian limit is very interesting. So it would be nice to get it directly without going through this.
Yes.
So at the moment, it's not clear where n, the number of particles, sits in here. In fact, it sits in this choice of representation mu. So this choice of representation mu is a partition of, but it's the following partition. It's k, n times. So you've got that in there. You sum over all other partitions. It turns out only a finite number of them are non-vanishing in this sum. And this is the answer. And the key bit was computing the partition function for the adjoint guy, which is buried in this paper here, which I have no idea.
Just to understand, you're imposing a UN constraint, and you're interested in the Lagrangian limit.
Yes. Yes. So the Lagrangian limit of this has actually been discussed in another paper I don't understand by Kirillov called On Dilogarithm Identities. Okay? And he has a very specific conjecture in that paper, which has subsequently been proven in certain cases about what happens in the Lagrangian limit.
If I were you, I would just look at the unitary matrix model and solve it directly in Lagrangian without going through it.
Let's talk about this, because I would love to solve this without relying on conjectures I don't understand. So the claim is the following. Take n divisible by p. So that's the number of vortices divisible by p. Take this partition function and send n to infinity. The claim is that the partition function of the matrix model in the n goes to infinity limit is precisely the partition function of the Westermüller-Witten model. It's the SUP Westermüller-Witten model of level. Okay. Where the partition function really means the vacuum character. Meanwhile, if you don't take n divisible by p, but you take n equals q on p, and then you send the n goes to infinity limit, you don't get the vacuum character, but you get other characters of the Westermüller-Witten model, where you compute the partition function, but where you insert a primary operator, which sits in the qth antisymmetric representation. So it's another character that's built on the qth antisymmetric primary.
Is this something you should have expected? What is the logical reason for it?
I expected it to be related to Westermüller-Witten model, but I'm amazed that we can compute and get this connection. This I think I do understand. It's because, if I said already, if I put a single vortex there, it transforms in the fundamental representation of SUP. And if I put p vortices plus an extra one, that state always transforms in the fundamental representation of SUP. In the ground state, that's right, but not all states transform. Just like here, not all states are in the singlets of SUP.
Yes.
So maybe the ones that aren't in the singlets are cancelled.
Don't pass.
Yeah, I don't know. Okay, so we have very, very compelling evidence that this quantum mechanics is capturing this Westermüller-Witten model in a very concrete way. The Westermüller-Witten model is a formal field theory that's defined by the primary.
Sorry, but the question is a bit simpler. I mean, should you have had any reason to expect that the partition function of the matrix model was the same as some character of Westermüller-Witten? Was there any reason? Not.
Here we should have realized in this case immediately.
Fine, calculationally. But I mean,
no, I think logically, even physically.
Yeah, tell me why.
So, we have this matrix model. There are two classes of excitations. There are those that sort of scale. There are excitations up to order n, and then excitations beyond that. The quasi-holes are excitations of order, I guess, n squared. Okay? But you can look at the small excitations, and the small excitations of this object are little ripples around the edge. This is true even classically of the vortices. So the vortices is some classical incompressible solution to the vortex ingredients. And if you want to deform them, the deformations are area-preserving deformations of that droplet. Just classical. So I think, yes, you absolutely expect these to be, you can see classically that they're edge modes, they're little ripples at the edge, they only go one way because of the magnetic field. So you expect them to be the chiral modes. And you can very quickly...
So you're saying that what you've got is quantum Hall is fluid, but only in a certain region.
Yeah.
And therefore there are edge modes, and there's this general expectation that the edge modes are Westermüller.
Exactly.
Okay, thank you.
So it's not all of the Westerminer-Witten. The Westerminer-Witten model is defined by the number of primaries. We've got all of the antisymmetric ones, but there's a whole bunch of other representations which have primaries that we don't have. So we're looking into seeing how we can insert states in the matrix model to somehow capture those. All right, so that's basically the story. And there's this very simple quantum mechanics matrix model, and it's clear it's capturing a lot of the physics of the quantum Hall effect, and in some cases capturing it in an analytically more tractable way than you can do otherwise. It's also clear that it's capturing a lot of the physics of the 1 + 1 dimensional conformal field theory on the bound. So I'm sure there's lots that we still can do here, but the question that we started with was how we can use this in a way to understand the grading of non-Abelian anyons is I think still the big thing to focus on. Anyway, I hope we have a couple of pages on this coming out in the next month or so. Thanks for your attention.
ICT has questions.
I can't hear you guys.
Any questions from ICT? We're not hearing.
No more questions.
Okay, thanks.
Sorry if the sound is a bit, this is beautiful and so on, but just to go back to the original motivation, this is not going to give you the wave function for the actual problem of electrons with their interactions,
Coulomb interactions,
and so on. So, as you've been emphasizing in your lectures and discussion, what this is giving me is something in the analog of the same universality class, right? But what does that mean? What can you hope to calculate from here that would accurately reproduce the physical problem? I guess you're saying certainly the excitation, the statistics of the excitations and so on.
Yeah, that's really it. Yeah. So the two things in the universality class are the statistics of the anyons, in particular the non-Abelian, and topological order if you put it on some manifold of
which is the degeneracy.
Putting this on a manifold, putting it on a torus, I suspect would be possible. But it's like taking D-brane physics. If you wrap dimensions transverse to the D-brane on torus, you do T-duality, right? So I think something like that might be possible for these matrices. But the first step is to try and just get this pretty.
The torus is likely to be more complicated than the sphere because you have to deal with the Wilson terms in the original Chern-Simons.
Think about just D-brane physics. If you take A equals 4 super Yang-Mills, which is just a D3 grid, I know how to describe that theory if you compactify two transverse directions on a torus.
With some infinite dimensional matrix.
Exactly, which then you T-dualize and you write it in 2 dimensions or higher.
Right.
On the dual torus.
Right.
I don't know how to do that for a sphere, and that becomes somewhat hard.
You don't know how to do that for a sphere, but actually, since you have an original field theory, the problem on the sphere will just be simpler because the reason you have to do that was the Wilson lines.
It's true, but the problem becomes constructing a matrix model which describes vortices.
Okay.
It's like asking for an ADHM construction for instantons on S4.
I
don't know how to do that.
Okay.
But I know how to do it for instantons on a torus.
Okay.
Sorry, I know this is actually an aside from the talk, so I'll shut up. But for Lagrangians or whatever, we know of a way to think of universality just by saying, look, we'll keep the most relevant operators which have some symmetries, right? And I thought there was a way of thinking like that for the quantum Hall problem which led you to the Chern-Simons theory because you're going to break parity and then the lowest order blah, blah, blah. So it's a bit... But is there a similar thing you can do just to wave functions? That is, one route might be start with the Lagrangian of interest, mess, write down the simplest Lagrangian with the right relevant property to operators, compute wave function. But here, here we did something else, right? We looked at vortices, which had detailed interactions different, but the statistics were the same, I guess. You wrote down the wave function. And then the other property should follow, I guess.
That's right. So the starting point was the universality that you mentioned. You write down Chern-Simons theories, and you start there. now we've quantized details of the vortices. So the details of these wave functions aren't going to matter, but the wave functions should be in the same unity. Which means you should be able to deform them continuously to the true wave function without going through some phase transition, keeping the gap state, basically.
One thing I think is worth emphasizing is that in terms of relating the matrix model wave functions to wave functions for n particles, there's no canonical map between those two things. There are many choices of particle wave functions which you can derive, because there's a certain arbitrariness in that process. I think
that's this problem.
I think roughly it's corresponding to something like the fact that we only have information about the complex structure here and not the metric. And if you want to get information about points in the plane, you need actually more geometrical information, which is just not present in the matrix. That's kind of the beauty of the matrix models. It avoids that.
It's worth stressing that the Carabalians did a couple of maps between this and this. This holds for both. This holds for both of them. So whatever map you do, it's between this and this always gives Loeffler at large distances, and they differ only by what's going on at short distances, which you don't care. So it's the long distance entanglement that's key in the Loeffler wave function to its properties. I think in new language, that's the point.
More questions?
So we talked about these gapless excitations, but what are the gapped excitations?
So there's a bunch. The gapped excitations are really the quasi-harmonics. So they're separated. The gapless excitations are the edge modes, which go up, I guess, to order n, and then the quasi-Hall excitations start at order n squared. They're kind of big swelling of the disk outwards, leaving some empty space.
Wait, but what you originally called the gapped excitations were putting more z's. Like those were the things that had.
Yeah, but they cost gaps because the whole thing's in a confining potential. So actually, the gapless excitations are, you should think of as Fourier modes around the edge. There's no constant mode, that's killed, but that's kind of a standard story for the chiral boson. And so, the gapped is gapped is because you get a very large object, and so it's 1 over n.
I see. You said you put more z's, you have just a bigger bubble.
Yeah, but each edge you can.
But that's the ground state. That's the ground state. Frankly, the number of phi's told you. The winding of the phi told you the size of the bubble. And then on that you could put more z's.
So you have the ground state. And then you can act on this with z baggers. I guess trace of z bagger to the n to the power n.
Right.
Okay. And so you can sum over n equal to d. Sum over all n's. So you should think of this as exciting the nth Fourier mode of a chiral boson on the object, dn times. And they cost energy, but it's momentum energy of this Fourier model.
You can go high enough, but it's all captured below. Right?
So usually in the standard quantum Hall language, projecting everything back to the lowest Landau level is kind of crucial in getting all these theoretic descriptions and so on. Is there an equivalent of projecting onto the lowest Landau level in this way of thinking about it?
I think the thing the matrix model is buying you is it's a description of the lowest level.
Of the lowest.
So anything you do is within the lowest level, which, as you say, is very hard to do often because if you do operations that take you out, you need to project out. So I think that's
so you think it's the automatic way of basically staying in the lowest.
Exactly.
So let me understand that. What was the original description of the vortices that had all Landau levels? The vortices were moving in an effective magnetic field, and you could have been in every Landau level.
In general,
the classical description of moduli space was in the lowest.
Classical description of the vortices? I probably misunderstood, but at some point I thought you said that the vortices were effectively like particles moving in a magnetic field.
That's true.
At that point, was the statement that they were effectively like particles moving in a magnetic field at lowest energy, or more generally?
It was a classical statement.
As a classical statement, it was all energies, right?
Yeah.
So then quantizing that should have given you more than just the lowest level.
Somehow restricting to the moduli space was nice. Certainly quantizing the moduli space gives you nice.
That's not true of particles in the magnetic field, right?
Yes, it is. it's because we have first order kinetic terms.
Oh, because there's no x dot square. Thank you.
Yeah.
Thank you. Thank you.
Yes.
Thank you.
It's this. Yeah. If we added as
So it was.
Z dot square.
Yeah. So it was classically, even the classical, just particles moving in the Lorentz.
Yeah, that's right.
Which makes sense.
That was built in.
It's Chern-Simons theory, which is the thing which you should only obtain as the
Yeah.
description of course.
Thank you. More questions? Okay.